Morning. This chapter is on timers and counters and timer counter applications. So in in our prior work, we've looked at relays and the other two items that were part of the original PLC package were timers and counters. So relays, timers, and counters were the original three things that had to be in a programmable controller to make it agreeable that we would actually be able to put a programmable controller into a factory instead of a those three items. So this was one of the things that was required from the early days. So you had to have relays, timers, and counters in order to have a real programmable controller. And that said, we're going to go through and we're going to look a little bit about some of these different timers and counters, but we're really going to talk about applications that use both, and we're going to find out a little bit about some of the details of each of these devices. And we're going to look at both the Allen Bradley and the Siemens on this, and we're going to look at some of the differences, but basically they have the same basic look and feel with these devices pretty much across the board. So we're not going to find as many differences as we are similarities, but there are some differences between the two. So we're going to look at those. And anytime you can look at the differences, you can say, oh, I see why that's important or why they did it this way or whatever. But at least you get an idea that two different companies approach something a little differently, but basically the same. So what did we have with old style timers? And this is something that we're going to talk about here. Now, there's a lot of old style counters, but they are all specialty. In most cases, they did a specific application, and I don't even talk about those in this chapter. But I do talk about in this chapter the old style timer, and this is the symbol for that timer. And an on delay had the arrow pointing up, and an off delay had the arrow pointing down. So this would be an on delay time to close. This would be an on delay time to open. So this would be a normally closed time open, normally closed time close. So this would be normally open, and time close. So these would be after the signal from the left turned on. This would, after the signal for the coil turned on, this one would close, this one would open, and this would be on an off delay. In other words, after the relay coil of the timer turned off, this one would open, and this one would close. So you had four different types. Now with these, we always talk about a timing diagram. So after the coil turns on, so here would be the signal for the energy of in the coil. A normally open, after a time delay, would turn on, or it would have turned off like this, one or the other. So here would be the coil, and here would be the energizing of the coil, and you would hear that click, and then you hear shh, because it's a pneumatic, an air-driven timer, and there would be a bladder that would actually, and then you would see the second click, and it would turn on here. Okay, so we have a picture of a pneumatic timer, and again, this is nothing more than a relay with a timer head on top of it. The irony of these timer heads is you had to commit to either an on delay or an off delay timer head. So you couldn't somehow change this from an on delay to an off delay. If you wanted one, you had to commit to that at the very beginning. You had to think your design out well in advance, or you had to carry enough of these around with you that you would, if you needed one but you wanted to change it to the other, you would have to physically unwire the one and wire the other one in. And that's been done, but this is not a cheap piece of equipment. This whole thing probably cost you $100 or more, and that's probably the price of an inexpensive programmable controller these days. But that's the idea of this one device. You could chew up the whole cost of a programmable controller with just one or two of these devices. This is the off delay at the end of the signal. After it turns off, then you have the delay, and then you hear the second click. And that's these two devices is the off delay. Okay, so the basic premise of timers is something after an on delay, something after an off delay, or in other words, after the signal turns on, something happens. After something turns off, something happens. Or this RTO, which stands for retentive, And that's the one that is a little different, very rarely used, but we're going to talk about that example as well. Now you see with Siemens, you see that they've got these two input devices, like this one right here. I call these the block ones, or they've got the little ones with the coils, the ones that look like relays. And what's the difference? Really nothing. Now, if you look at the differences between the ones with the square, the rectangular ones, and the one with the relays, you're finding that they're absolutely the same. It's just the way that they look and that the way that you are allowed to program them. So what are the ones with the circles? Well, these are the ones from Chapter 1 that we talked about that were IEC 61131-3 compatible. So Siemens has put those all in. Allen Bradley has not, although they claim 61131-3 compatibility. Are they lying? You decide. I don't really care about the idea of it. Now, what is there about 61131-3? Well, supposedly, if you have a program written by a programmer and you have one programmable controller, you can take that program and you can put it in another programmable controller from another manufacturer and it will work. Again, that's not necessarily what's going to happen, but that's what's hoped for. And it doesn't mean that you're going to get that, it just means that it's hoped for. But this article tells some of the good and the bad about that. It's the end of Chapter 1. If you want to go back and read it, you can. It's interesting, but yet we're just going to ignore the ones with the circles because the ones with the rectangles are the better ones, and they're the ones that look the same for Allen Bradley and Siemens. And to be blunt, they work just great. So that's the basic premise: is we're going to look at the rectangular ones, and we're not going to look at the ones with that look like relays. So there's a separate one that Siemens does that's a pulse one, and you can build a pulse from a retentive or from a TON timer, and you don't have to have the ability to program a pulse as a separate entity, but you can if you want to. Now, just to tell you that these timing diagrams are your key to most of these things. So let me just say this. Allen Bradley doesn't have one that does this exact same thing. Okay? They don't. You can build one from a TON timer. Is there any penalty for doing that? No, you don't. You decide how you're going to handle it. But what you do is, for Allen Bradley, is you put a one shot here, and then you basically start your timer off with a one shot. So that's the difference, is you fire a TON with a one shot, and that gives you this ability to do this or this, and it gives you a pulse of a certain duration. So again, you can live your whole life with TONs, and you can ignore TOFs for the most part because you can use a normally closed contact. And you really just need to know two. You need to know a retentive timer, and you need to know an on-delay timer. And those are the two that you can get through all your programming with, are the TON and the retentive timer. So this is the TON timer. The TON timer does not turn on the output until the delay. And this delay is in milliseconds, and there's a number. So if I have 500, that's 500 milliseconds, or half a second. If it's 1500, that's 1.5 seconds. So you can basically control this based on a number down to a millisecond. Here's one that didn't make it, and it turned off, and then basically you have to start over again. So these start over again every time you turn on your signal. That's the difference between a retentive and a non-retentive. This is a TON is a non-retentive timer. It does not remember. So how do you energize it? Well, here's the block. You say, okay, turn this on, and this starts the counter. This starts the timer timing. And then when it gets done, it turns on here, the Q. So you can have a coil over here that says, okay, 200 milliseconds after this turns on, this turns on. You say, well, what does that really mean? it's a delay. This is a delay of 200 milliseconds. This provides me a delay of 200 milliseconds between here and here. And that's basically how this works. Again, the off delay we can ignore because why? Well, you can take this signal right here and make it anomaly closed, and that makes this an off delay. Okay? So the delay from this signal to here would be, if I wanted to do the off delay of this signal, I would make this anomaly closed and use the TON for the off delays. So again, you do not have to remember off delays, except for the fact that sometimes somebody does program one and you have to go back at that point in time. Very rarely do they do this, but very rarely do you ever see that an off delay. But you might have to go back and reconstruct. So you might have to look at this timing diagram to be able to reconstruct it if you were putting it in another language. But that's about it. TOFs you can ignore. This is the one that is the retentive one, ONR. The time delay on retentive is this one right here. Now look at what happens. What's the difference? Okay, so this gives you a little bit of the time, then you're not timing. This one gives you a little bit more of the time, you're not timing, and this one gives you the rest, and then you're done. So basically, your preset is after the accumulated amount of time of this plus to there. Okay, and that's it. ONR. RTO is the Allen Bradley equivalent. So ONR, on retentive or retentive time, or RTO, are the same. ONR, RTO are the same. So now what do we have? We have the same thing with the 62131-3 instructions. We're going to skip those. They're the same. Okay. So this is a reset timer. How does it work? Well, it works like this. Like if this turns on and it doesn't turn, this is your preset. So again, it turns on, turns off, turns on, turns off, turns on, turns off, and finally it turns on, and then this turns on. But it accumulates times. Excuse me, no, this is the TON, I'm sorry. This is the on delay timer. So every time this turns on, if it doesn't reach preset, it goes back to 0. The elapsed time is over here. Now, the difference between Allen Bradley and Siemens also is these two tags can be, if you do not need this variable in your program, leave it alone. If you do not need this variable, you have to fill it in with a number. If you want it as a variable, declare it as a variable. If you want to just have a preset number in there that's always that preset number, put it in there. So you can either make it as a variable or you can make it as a number. But it's entered as a number, an integer number, or as a variable, which you can then fill in the variable. Okay, how do you reset the timer? Well, here is the RT, reset timer. This is the one that allows you to reset that. Okay. So this is one of the circle ones. You don't need this. You don't need this one at all if you have this one up here. So just use the block ones. Don't use the circle ones in your set. Now we're going to come up with counters. Counters are a little different in that there's two basic types of counters. There's a number of different ways that you can do it. You can count up and you can count down. Or you can have a single counter that can go either up or down. We're going to talk about examples of all those. Also, you have this idea of what does it take in order to count? Well, this is a scanned program, right? It's a scanned program. So if you scan your program and you see the input as a 0, Next time you scan it and you see the input as a 1. That counts you 1. So on each leading edge, it counts. So if later on that bit turns back to a 0, then you're primed to, when you see another 1, turn on it, it counts again. So the pulse has to be at least the length of the scan rate. It cannot be so fast that you can miss one. If you can miss one, that negates the use of this counter. You say, well, how do you count high-speed pulses? Well, most programmable controllers have either a high-speed counter card, or in the case of the Siemens, it has it built right into the first 6 inputs. You can count high-speed inputs on the first 6 inputs, and they will count high speed. So what does that mean? That means there's an extra piece of hardware, either as a chip or a built-in counter in the firmware, that allows you to pick up pulses at a higher rate of speed. So with the higher rate of speed, each time I read the inputs, it zeroes that count out and takes the count of the pulses that happened since last time you read. That's different than this counter. The counter that we're talking about in this chapter, chapter 7, you have to see an off to on transition. You say, well, that's confusing. It is, but don't worry about it for the most part, because you're either in one camp or you're in the other. You're either in the camp of saying, I have pulses that are coming in from devices that I want to count. I'm counting boxes. I'm counting people walking by. I'm counting something that I have a good signal coming in from, and then I'm going to be counting these things that are going down the line. That's different than counting high-speed pulses, where there might be 500 pulses per revolution, 100 pulses per revolution, 1,000 pulses per revolution, and each turn of the shaft of my motor, I get another 1,000 pulses. Very different applications. So you're going to be looking at this from 2 different points of view. And you say, well, where is the pulse counter stuff? It's coming. It's in a later chapter, and we're not going to talk about it here. But that's the difference. So they talk about this idea of a CV and a PV. What are those differences? Process variable is my preset. CV is my what's actually happening. That's the count, the active count. And the Q is the bit that turns on when the output is reached. So that's the difference between those variables. Okay. So this one is a counter, and notice with counters you have to have a reset somewhere in them. This one counts up. This is my preset, and this is my active count. If I don't need this information, if I just need to know when it comes to completion, I can leave this blank. I can put this in. I have to put either a number or a variable here. And for my reset, if I want to reset this scope to reset back to 0, this is going to count up. This is CTU, counting up. So when it gets to, like, if I set a preset in here of 50, and I get 50 off to on transitions, this output turns on. Q turns on and turns on this relay. That coil, and that's how it's done. You do not have to have the CV unless you need to know what the active count is at an instant in time, and most of the time you put a variable in for that. And most of the time these are 32-bit numbers, not 16-bit numbers, but you can have either one. So they have a countdown as well. So I can count down as well as count up, and this is a programming block that can do the counting down. How how do you count up and count down? Well, with Siemens, you use a CTUD, which is both. It's got the ability to count up and count down, and this one can do both. Now, we're going to talk a little bit about how Allen Bradley does that in a minute, but this one has everything built in. With this, you count up. With this, you count down. With this one, you reset. With this one, you then, when you turn this on, you actually can load another variable in here. In other words, it takes a new preset. So this one allows you to change this one. You can put a number in here, but it doesn't change until you toggle this on. You toggle this on, it loads this new number into the preset. So this tells me what my active number is, and this tells me whether I'm counting up or counting down, and this tells me am I done, and did I reach my preset? Okay. So can you go negative with these? You sure can, and you can go above the maximum as well. All right, so this is the, and we have a lab with both timers, and we have a lab with counters, and we're going to talk about those in a little bit. So this is the layout for the older style timers. And again, this is a 16-bit process, and you had a 16-bit number for your preset and a 16-bit number for accumulated. With the newer ones, it's 32 bits. So you had these 3 bits designated enable, EN, Siemens is IN, but Allen Bradley is EN. They had a TT bit, which is the difference between I'm in process, I'm not done yet, and then the bit that's the done bit that turned on if you were actually done. Now, when you program these, you don't have to program the EN and the DN. You do not have to do that. The EN is when it turns on over here, the EN turns on over here. The done is when you're done. In other words, when you reach your destination, and it just stays at that value. Okay, so these are like a deck of cards, T40, T41, T42, T43. What's wrong with that? Nothing's wrong with that. These are dedicated timers. There's no name associated with them. You have to come up with a name yourself, so you have to put that in as a comment. So the name was not the variable name that you called it. The name is T40, but you can put a comment with that. The comment does not go into the processor. The comment just stays in your computer. But the thing that goes into the PLC is the number T43. So again, a little bit of the old style, but that's how the old style worked. And this is an example of that. This would be a flashing light, 2 timers, and if you look at this, this is how timers work. How does this thing start? Well, it starts with this off, and you get power here. So you get power to this when this starts timing. It goes up to 1 second. This is a time base of 1, so it goes 1 second. It turns on here. The done bit turns on, and it turns on down here. Then you have 1 second here. So what is this? This is a 1 second flashing on, 1 second flashing off light. So you got an on, off, on, off. You get 2 timers for that. The retentive timer, here's the retentive timer. Now what's the difference between a retentive timer and the non-retentive timer? You have to have a reset. So with Allen Bradley, the reset is a separate coil down here, and that's something that this could be located anywhere in your program. You can totally have this separated by pages, and that makes it hard to know exactly what, but you got to remember that this is going to be there. Okay, so that's the reset. Okay, so how did you do the old style timers and counters? You had to chain them together because 32767 was not a very big number, whereas the new numbers is 2 to the 32, which is a big number. So that gives you the ability to go very, 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 very big. So this is counters, and this is all the bits for counters. So again, count up, count down. Now Allen Bradley is unique in their counting. So the counting up and the counting down, this would be you can count up with this and you can count down with this one. Or you could have where you could actually do both at the same time, and I'll go through that in a little bit. So this is the compact logics and the control logics timers and counters, and this is an explanation of that. Notice they don't have a lot of them, but they have everything you need. Right here is that you have to declare a variable for this, and when you declare that variable, you get all the parts that you need with it. In other words, you get the The name, everything, and that's the way it is with all of theirs. You declare a name, a variable name, and that variable name gives you all the abilities that you need. Okay, they have the same TON, the TOF, exact same as Siemens. The retentive, they call it, instead of ONR, they have RTO. So RTO is the retentive timer, and this is that. The retentive timer, and here's my reset for that retentive timer. So this name here and this name here have to be the same name. Same tag to both places. Okay, so this is the same type circuits. Now, how do you use this? Here is we go to the store sometimes, and we go sometimes to the drugstore and we get a twofer. What is a twofer? Well, this is a seal circuit that, look what we've done here. We've taken the enable bit, which is the bit that comes to this point, and we've done a seal circuit, which is a memory circuit here. So you push the button, what happens? It stays on, doesn't it? It stays on until you push the stop button. But you also get what? You get a delay of 1,000 or 1 second. So you push the button, a second later, the done bit comes on. So if you need a circuit that has that capability, memory and delay, you got it with this bit right here. So this can be used as a coil with the enable bit. Notice that, and this works with both processors. You can, either with Allen Bradley or Siemens, you can do this, okay? What would be the bit for the Siemens instead of the .en? .in. Same thing. Okay, so here's the counter. Name, preset, accumulated. Okay. So, how does Allen Bradley do counters? We're going to talk about that here. This is, again, some examples of counters using the compact logic programming. This is a seal circuit with a delay that says, okay, how do I get a circuit to turn on? If it's a pump, I can say, I just push the start button and it runs, right? Well, in this case, there's a sophistication level to it in that we have a pressure switch. The pressure switch has to be met before we can continue to run. But if I push the button, I want a delay of a certain amount before I actually allow the pressure switch to turn it off. So this is that delay. Okay, so I push the button. I have this method of going around this pressure switch, and it gives a time delay. This is 500 or half a second. So this is giving the pump a half a second to get up to pressure. Now you may want to make that longer, make that 5,000, make that whatever you want, but it gives it a little bit of time to go around the pressure switch. And now when the pressure switch gets to high pressure, you're running through this, and this is gone. This is open. This circuit right here is no longer part of the circuit. So that's a way of having a pressure switch or a high switch that you have to satisfy to continue to run, to allow you to start up before, and you push the button and you can walk away, and you know that the pressure switch in 5 seconds or 10 seconds is going to take over. That's a good thing. How would you build a dam in the West out when they built all the Grand Coulee Dam and all these various dams in the Hoover Dam? They provided an alternate path for the water to flow, didn't they? They allowed it to go around, and then after they got the dam built, they made it go through the water to go through the dam, and they get the highly directed power out of it. So basically, it's the same philosophy. You provide an alternate path for a short period of time, and then you make it go through the one you really want it to go through. So this is a physical example of that process where you allow an alternate path and you make it go through this after a while. Okay? So that gives you an idea how timers can be used with seal circuits. And this one You can use timers here to allow you to have a delay if you add some what we call uh, level switches. So we're going to add some more parts and pieces to this. And what we're going to add is we're going to add a speed switch. Now a speed switch is at the other end from where the motor is. Here's the motor on a conveyor. Here's the speed switch. Okay, now how do you construct a speed switch? Well, if you have a proximity switch and you have a little tab that rotates around, look what happens. Every time this tab rotates around, it sees a 1. So this is seeing this metal. That's this proc switch right here, proximity switch. So you're going to see a timing diagram that looks like this. Every so often it's going to turn on and it's going to turn back off. What is the definition of run? Off to on, and then a little bit later off to on, a little bit later off to on, a little bit later off to on. What would be a bad situation? Either it's always off or it's always on. Either way, it's bad. So how would you determine whether you have a run switch or not? Okay, how would you know if you have a run switch? Well, you would have to be able to look at that switch and say, okay, I'm going to be able to see an off to on transition. We're going to build that later. Okay, so also you also want to have when you're taking from one to the other, this hopper, the downstream, you want to be able to if there's a hopper that gets over full, you want to be able to shut it down as well with that. Okay. So we want to have delays in these places if you have those kind of problems. Okay. Now another thing about time is, well, I can build a clock with timers. And while that sounds attractive, don't. There's an inherent inaccuracy in timers that if you try to use them as clocks, they don't work. So every time you reset a clock with a timer, it takes that scan delay to reset, and that's lost to your clock. So how do you keep accurate time in a programmable controller? Well, every programmable controller today has in it a built-in clock, and you can read the time of day, and it's very accurate. You don't need to rely on timers to get an accurate time of day. So that's good. The old time had with the Allen Bradley, the Slick 500 has these locations. You can do the same with the modern day, with the more modern clocks. You can Google them and you can find them what is the time of day. You can find it. Now another part of this is if I have a number of programmable controllers, how do I know that the clock that is in one is the same as the clock that is in another? How do you know that? Well, there is a sophisticated level of time stamping between programmable controllers that you can actually cause all the programmable controllers to be time synced. And most programmable controllers today have that. Why would you need that? Well, it's because if there was an accident or something went wrong, you want to know timestamp when it went wrong, right? But you want to know based on all the programmable controllers where that it happened and what was the status of each of the programmable controllers at that instant in time. So not only do you want to know for that one time what happened, but you would want to know for all of them. So you want to have all of them. If you have 4 or 5 programmable controllers that are in a process, you want to know that they all have the same time, that they're all looking at the same thing at the same time. So I have an example of that. We had a illustrious mayor in the city of Toledo, Carty Finkbeiner, and whether or not you knew him or have ever heard of him, he was the mayor twice, and the first time he was the mayor, he had this idea that he wanted to put flags on the Cherry Street Bridge. Well, maybe you did or maybe you didn't know that the Cherry Street Bridge is run by a programmable controller. Up and down of the controlling of the Cherry Street Bridge is done by a programmable controller. they actually take the program controller and they run a cable down on the riverbed, and it goes back up on the other side, and then basically they have a remote I/O on one side, and they have the program controller on the other, and you can see that it's kind of a complicated process, but they have it and it works. So how do I know about this? Well, I was a helper at one point with a program that actually was being done to make this process update. So they were updating the program controller at that point in time, and when they did, there was another guy that actually did it. I was just a helper, and I didn't. It was not a big deal for me. But anyway, so 6 months or so after this was all installed and up and running, somebody was walking across the bridge, and it was a lady, and she got out on their bridge, and the tender, the person that raises and lowers the bridge, did a visual inspection and didn't see her because she was behind some of the flags. And he proceeds to raise the bridge because there's a ship coming. So this woman, instead of being able to walk across a flat surface, now is walking on a inclined surface, and she takes a slide. It's an elderly woman, and she slides all the way down into the inner workings of the bridge. Fortunately, she does not get hurt. She's okay. But sometime after that, I called this guy. His name is Roger, and I called him Roger. I said, Roger, how did this ever happen? Whatever. He said, he was down there within 2 hours, and they had a printout that showed exactly what happened. It was the tender, the person who pushed the button, that made this happen, and they had timestamps on everything. So are timestamps important? Oh, you bet. And they proved that it was the tender that did it and how they did it and all that kind of decision making. There were no questions how it was done. But timestamping of events can be extremely important. So again, I just want to let you know that this is an important concept, although you just have to look it up. It's not something that we're going to talk about in this course, other than just now. Combining of timers and counters. So you can have a timer and then a counter and that type of thing. So if you're counting something, you can actually say, I'm going to have a little bit of a delay and then count it, because I want to make sure that signal is a real, true signal. It's got to be on for a certain period of time. So at least half a second or whatever, that gets that kind of you say, I want to make sure that I've got a part there before I count it. Sometimes proximity switches can be extremely noisy and give multiple inputs, so you want to definitely do this when you're counting parts. So that's what that is. You see some inputs before you actually count, and the count doesn't occur until after it's been on for a while. Okay? Now what's wrong with this? Okay, sometimes the counting aspect of it is really good, but at other times you want to act on this. Because if you always put a timer in front of an input before you actually act on something, what have you done? Your program is slowed down by this amount. From here to here, your program is slowed down. So if you're making parts by the hour, you just slowed your process down for making that part. You don't want to do that. You want to act on when you see the first input, usually, if you're doing an automated process. However, if you're doing a count, to see for count for parts, you want to do it on this one. So there's a big difference between the two ideas. I want to count parts, or I want to start at the next step of my process, use this, because that's where you first saw it. Or maybe split the difference. It's up to you. Okay, so can you have a race between a timer and a counter? And the answer is yes. And the example of this is a good friend of mine had a program that he was running on his panel, and he was very sensitive about the fact that he didn't want somebody to start a new batch until he was sure that they really wanted to start a new batch. So I said to him, Nate, how do you start a new batch? He said, come over and I'll show you. So he had a push button. It was a button that was, you would either, it would stay up or it would stay down. It was called a detented head push button. You could go up and you could go down. It was hard to push, by the way. And he said, you have to push that button 3 times in 2 seconds. So what is he saying? you really have to want to make a new batch in order to make it run, because it took a physical, quick type action to get it to work. And he could show how to do it, and it was kind of funny to see it actually happening. So there are some times that there are buttons that you really don't want to push unless you absolutely have to. And again, what do you have today? Well, you have passwords, and you have, do you really want to do this? Do you really want to do that? And you ask again and again and again until the person says, yes, I really, really, really want to make a new whatever. So that's done that way today. But this idea of a race still can be used, and this would be an example of a race. And this would be the counter is racing the timer. And if the counter wins, you set the bit. If the counter loses, the timer wins, you reset the bit. So again, can you have a race? This is a race of 2 pulses in 2 seconds. And it works. So you set 2 people going 2 different directions, and they get to a certain point. Who gets there first? One guy wins, or the other guy wins. So if the one guy wins, if the counter wins, Mr. C wins. This is the bit that's set. If Mr. T wins, the timer wins. This bit is not set. Your choice. You say, is this ever used? It can be, and I'm going to say to you that at holiday season, Christmas time each year, there is a sale that goes on every year. It's called the clapper. And what is the clapper? It's this. It's really this circuit right here. So if you want to know how the clapper was written, if you had a program controller, something like this. So this would be the sound from the clap, the button. Clap on, clap off. There it is. So there's another one here. This is in the lab 7.1. Add a switch embedded in the road. See if there's a backup of cars. If cars are going by and they're going by at a very slow rate, it means they're backed up, right? So you would do one thing if there was a backup. If they were going by quickly, you would do another thing, and you would say, I'm not going to reset. I'm not going to set a longer time duration for my preset. Otherwise, I'm going to go with a longer time duration. In other words, one way short time duration, other way long time duration. But this would be like a clapper. Okay, here's another one. This is a project for stacking or grouping of boxes. So I have boxes that come onto this conveyor. You push a button, forklift driver puts the box on there, and it's going to go down this conveyor, okay? It goes down this conveyor, hits this photo eye, and then it goes onto this conveyor. What we're going to do next, we're going to group the boxes on this conveyor. So 1 goes by, goes down here. 2's go by, what happens? 2 go by, and then they're grouped, right? 3, 4, etc., etc. And at some point in time, you're going to say, okay, now after so many of these, I'm going to put them over to this conveyor, which is conveyor 3. So I'm going to convert this conveyor from a loading conveyor to an offloading conveyor, and I count up, then I count down, and then I go back to being a loading conveyor again. So that's how that's, we've talked a little bit about how that's programmed, but that's how that's done. Here's another one. We've talked about this one before. You start the push button, put a part on this conveyor, it goes down. At this point in time, it gets sanded. What do you do here? Well, you have to dwell a little bit. If you don't dwell a little bit, you're going to tear your machine apart. So you have a dwell, and then you go back, and then you start back. So basically, you go down, you hit this photo eye, you dwell a little bit, and then you start back. So you let it stay there for just a little bit, and then you start it back, and it stops. Okay. So after all this, how did the old fellow, the guy that did the first timers, how did he do this? Well, interestingly enough, Modicon was the first to come out with these timers, and they basically had one timer, and if you wanted a retentive timer, you had a separate entity for this than this. If you wanted an on delay, a non-retentive timer, you basically tied this to this, and that would be a retentive timer. A non-retentive timer would be, or excuse me, a non-retentive timer would be tie this bit to this bit, and then have one contact up here. If you wanted an off delay, make this a normally closed contact. If you want an on delay, make it a normally open contact, and that was it. When a time turned on, this would turn on over here. So very simple. There were really three timers, 1.0 second, 0.1 second, or 0.01 second. So they didn't have the sophistication of the 32-bit number, but they basically just had one timer, and that was it. Very strange, but that was it. One timer. Total one timer, and that was it. That's how it's programmed right there. So you can make it that simple, and that's all you really need to know is that you could have it like that if you wanted it. So this is the summary of this chapter. Now we're going to go back and we're going to look at the chapter a little bit more in depth, and we're going to do some problems, and we're going to do some labs, and we'll get onto that. Okay, we're going to work on problems at the end of chapter 7, and we're going to go through the problems and see what we got as far as starting on page 44 of chapter 7. So number 1 is a Dbound circuit. And so I have an input that does this kind of thing, and I want to only have it on if it's been on for more than half a second, so I have to wait until it's been on for half a second. So what you have to do there is have an input that goes through a timer, an on delay timer, and half a second is preset of 500. And that would give me an output that would go to a coil. Let's call this coil A. This would be my input, and this would be A. And everywhere I previously had used the I, now I would use the A. Okay. Now, it says limit switch 1. So the limit switch 1 would be my input. Limit switch. So that would be my limit switch right here. And this would be my contact that I would use. Now, what's wrong with this circuit is that if you are working on a cyclical program, you do not want to do this. This is only in cases where you're doing something that is non-time sensitive, and you don't have to do it. Now, there's also this idea of filtering. So you can have an input, and you can say how long does that input have to be on before I see it as a 1. That's called filtering. And filtering is available on most programmable controllers, so you can actually test to see how long you want the input on before it sees it as a 1. And that's something that is set by your configuration of your I/O. So that's another way of doing this, but that's not what's being asked for. This is what's being asked for in this problem. All right, so we're working on number 2. So problem number 2 is, for the following circuit, answer the questions below. So we have a circuit, and we're looking at this circuit with a normally closed from the second timer, and it comes to the first timer. This is an Allen Bradley design, and we have a TON here, and we have a timer 1 called first, and I have 1,000 in here. So the preset is 1,000. And then these 2 bits at the end we don't even have to program because they come along for the price of admission. So then when the first one comes along, it turns on the second one. First dot done turns on the second one, another TON. That's the second one, and that one has a preset of 500. So 500 is the preset of this one. And ask the question, how long does the light stay on? Well, you have to look at the bit that is being asked. So this one is on for 500 milliseconds. So while this one's timing, it's the .tt bit. When that one's timing, it's the .tt bit. So when it's not timing, the not timing of the .tt bit of second is on for 1 second. And it's on when this one's doing its timing. How long does it stay off? Well, it stays off for the time here. So this would be the on time. This would be the off time that it would be doing that. Modify the circuit so the output is on for 1.3 and off for 1.2. So this would be my off. This would be my on. So if I wanted to do that, I would say 1300 up here and 1200 down here for my presets. And if it says on for 2.5, that's 2500. And off for 1.7 at 1700. So that's the answers to those. So C and D. So this would be C. This would be D. Design number 3. Design a circuit that turns on a latch when a button is pushed 3 times in less than 2 seconds. So what does this sound like? It sounds like a race, doesn't it? So we have a button, and it starts what? Starts a counter, CTU. Okay, so here's my input, push button, and it starts this counter. When the counter is greater than 0, okay, the counter greater than 0, greater than 0, so the counter, let's call this counter 1. When counter 1 dot ACC is greater than 0, we start a timer, TON. Now if the timer times out before the count goes to 3, so we have a preset up here of 3, we reset the counter. So we turn on, okay, this is 2 seconds here, and we have a, so if the counter times to preset, okay, so count 1 dot done turns on a bit, and we're going to call it a latch bit, or we could call it a set bit or whatever. Let's call this when, and if it is, okay, so that would be if this is if you do get to the 3 counts in 2 seconds. If you don't, the timer done, this is timer 1 dot done, then we reset the counter. So this is pretty much Allen Bradley, but if I were to do the same thing with Siemens, my reset would just be up here. I would have a bit here, and that would be my reset. For my counter up. And instead of the greater than is the same, and the timer is the same. So basically this would be the same in both. And instead of a latch bit, we would have a set bit for the when bit. So that's basically the Allen Bradley. This is the Siemens differences. Okay. So that would be how you would do number 3. Number 4. A low pressure switch is to add it to a fan starter circuit. So we've talked about this before. This is like the dam and the alternate way around it. So we have a stop switch, and we'll use it as a normally open because we know that the switch is wired to a normally closed. So here is my seal, and here is my pressure switch. I'm going to use a normally open because this pressure switch would wire to normally close. And around it, I'm going to put a timer. So when the timer is done, okay, so this is be my fan. This is my seal, and my start, and my stop. And then this is my low pressure switch. Okay, and this would be a timer. So when the fan turns on, it starts a timer. And when the timer is done, timer 1 dot done, or Siemens would be dot Q. And that would be it. And you'd give this maybe 10 seconds. 10,000 would be my preset. And that would be it. So that would give you an answer for number 4. Number 5, very similar to number 2. So it's like, can't write today, but we'll go back. Like number 2. So just do number 2 again and you'll be okay. Number 6. Number 6 is a chain of timers. So 1 turns on the first turns on the second turns on the third. If this one turns off, they all collapse and they all go back to 0. So before you turn on anything, this would be K1. Then after a while, you would turn on K2. Then you turn on K3. And then the done bit over here would be K4. Okay, so basically, when this turns on this. Delay turns on this. So delay turns on this, delay turns on that. So what would I say here? Well, K2 is the done bit of, this would be timer 1. This would be a TON, a TON, a TON. And this would be a Q, or a .done bit. So this would be the .Q. So timer 1 dot Q, timer 1 dot done. This would be equal to timer 1 dot Q, or timer 1 dot done. Then this would be timer 2, and this would be timer 2 dot Q, or timer 2 dot done. Siemens, Allen Bradley. So K3 over here is equal to timer 2 dot Q, or timer 2 dot done. And what does K4 equal? Timer 3 dot Q, or timer 3 dot done. All right. That's it. That's how you do number 6. Okay, so we're going to skip number 7. Number 8. Okay, so how many parts are going by a certain point at Okay, so the counter is pulsed for each part, which is counted to an input. So here's my counter, here's my input, input 1, and it goes for 60 seconds. So we're going to count up for 60 seconds, CTU, right? The accumulated value is over here. We're going to call this val 1. Val 1 is my accumulated value of parts. So if I count for an hour, that'll be the number of parts. Okay, so it comes out over here as my output. Now that's Siemens. Allen Bradley would be .acc. So it would be count 1 .acc. So either way, these are equal. This would be Siemens, this would be Allen Bradley. So what do you do with this? Well, at the end of 60 seconds, you want to store this. Okay. So you basically, at that point in time, want to save that value, and you don't allow any more of this to happen. So basically, once you start, so you have a switch down here. So you have a switch, and you go for 60 seconds. So this would be a timer, a TON. At the end of 60 seconds, you have the done bit, or the .Q. Okay, so 60 seconds. Timer 1, 60 seconds. How many counts would that be? 60,000, right? Okay, so you do not allow any more counts to come through after what? Timer 1 dot done, or timer 1 dot Q. Okay? When it's done, it's done. You flip the switch, let it rip, then it stops. Now if you want to reset it, if you want to reset the counter, you do what? The switch goes off, and you do the reset. Well, how do you reset the counter? With Allen Bradley, you do an RES. With Siemens, this is Allen Bradley. With Siemens, you do the reset right here, the reset right there. That's the Siemens approach. Same thing. I'll let you work on the average and all that sort of thing. I'm not going to worry about that. Rewrite the number 9. Number 9. Rewrite the controls for the diagram below using the new actuator function table chart. So what do we have now? We have the running bit. So the running bit is a bit that's either on or off. So basically, in this case, we turn it on, and then we let it time for a little bit, and then we allow for the running bit. So the running bit has to be delayed from the run. So I tell it to run, and if it's running, then I'm okay. So basically, each of the 3 conveyors have to have the following additional circuitry. The start, the seal, it's running, or the time delay. So you have to have the time delay. So this would be conveyor 1, conveyor 2, conveyor 3, and the time delay around it. So the conveyor 1 bit, you have to let it go for a little bit, TON, like 5 seconds. And after that, T1 dot done, or Q, and then it's running. So this is the circuit that you have to add to each of the 3. That's what we had before. So that would be the answer to number 9. Okay, number 10. When this counter counts to preset, the number of boxes has counted to 4, and the boxes are now ready to be moved as a group to a 3rd conveyor. a second conveyor or a down counter with the same address as the up counter. Write the code that moves the boxes off the conveyor. So how do you do that? Well, what moves the boxes onto the conveyor is the up counter, so the down counter is the one that moves the boxes off the conveyor. So here would be my photo Y2, and they do a down count. Or, okay, so they do a down count of the boxes. All right, so I have the down count, and that would be preset of 4. And when it gets to 0, it turns on, or the done bit turns on. So basically, that's all you would have to add to that. Number 11. So this is the microwave question. So when I cook my oatmeal, I have a microwave, right? I have a mess right now. So I have a microwave, and it says to turn it on for 1.5 minutes. So I'm going to be turning that on. I want to open the door of the microwave, put the oatmeal in there, and I'm going to set it for 1.5 minutes, right? 1 minute and 30 seconds. Okay, so that's 90 seconds. What kind of a device do I have here? Well, I have a door that says it's closed, and I have a retentive timer on, timer, or an ONR. This is Allen Bradley, ONR, Siemens. Okay, so what do? I set this for 90,000, right? Now, if the light turns on, I interrupt this. In other words, if the photo eye turns on, I turn this off. And when the photo eye turns back on, it goes and it continues to go. So this is my door. This is my photo eye. So every time the bubbling up starts, it stops it, and then when the bubbling goes down, it continues on until it goes to the, and that's it. So this is one of the only examples that I can think of that you would actually use a retentive timer for. Very rarely do you use retentive timers, but this would be one of those situations where you would do that. The done bit, excuse me, the door is closed, and you're running. This is the run, but if the photo eye says no, then you turn it off. You turn off, you have to stop the run. And then when the bubbles go back down, then it goes back on again. So that gives me a methodology for turning on a microwave and not dirtying it up. All right, any questions about that? Good question. The oatmeal question. And number 12 is very similar to number 1, so we're going to skip number 12. Number 13. So, how would you answer this? Here's your timer, and here's your TON. So here are my bits for the Allen Bradley. Okay, I've got the timer 1, timer 0, dot EN, the Allen Bradley side. What would be the Siemens side? Well, you can call it a TON. Timer 1 or timer 0 dot, dot timer underscore 0 dot IN. What about the done bit? Timer 0 dot done. Timer 0 dot Q. What about the timer timing bit? There is no bit. So you have to build it from scratch. You have to say timer 0 dot IN, but not timer 0 dot Q. And that gives you the same. Okay? So that gives you the same for that one. Number 14. Same thing with counters. Counter up, down. So we have a Siemens counter, CTUD. So it's called CTUD, whatever. Let's just call it CTUD, or let's just call it counter 1, CT. Give it a name. Okay, counter 1. So this gives me my up count. This gives me my down count. This gives me my reset. And this gives me my load. Now what does load do? This gives me my PV, which is, the PV is the preset. And CV over here. And tag out. Do not know what D means. And tag out over here means done. Okay, this would be my up count, my down count, and that goes to 0. When it's equal to 0, this one turns on. So basically, this would be my done bit. This is my done bit right here. Okay. Now, how do you do that with Allen Bradley? How do you do both of those? Well, there is no count up down counter. So you get one counter that you can designate both as a CTU and a CTD. So CTU, if you say CT1, counter 1, and it has this count up, or counter up, let's just call it counter up. Count up. So I have another one called CTD. The same name. You only get this once, but if you have the same name on both of them, this works. This one does the countdown. The preset is the same one for both. The reset is a separate coil. And the load, the done bit, is the same for both of them. It's automatically built, so you don't even have to worry about it. But the reset over here, this load would be if I wanted to load a new preset. So my preset, CT1.pre, is inside here. But if I wanted to load that, I would have to do a move of the value into CT1.pre. That would be my load. It's a move block. So we haven't studied move blocks yet, but that's how it would be done. So this is how Allen Bradley does a counter up or downer. This is how Siemens does a counter up or downer. You say, now what do we care about counter up or downers? Well, in lab 7.2 you're going to do one. So you probably ought to take some time to look at this one. Okay. So number 15 is a question of a timing diagram. And what kind of a timer is this? Well, as you can see, it's the retentive timer. So what would be your answer? So from Allen Bradley, it is a ONR, or excuse me, from Siemens, and an RTO from Allen Bradley. So that is the answer. It's a retentive timer. You have to recognize that from the fact that it starts up and goes across, starts up, goes more. What did I call this in my? I call it the oatmeal timer, or the oatmeal timer. Okay. Number 16. Using something other than a PLC instruction, how do you do counters without a counter? Well, we haven't seen this yet, but this is an add block. Add block. But instead of the input being the solid input and we're looking for a leading edge, we have to do what? We have to make this a leading edge, don't we? So if we do a leading edge or a one-shot, then an add block is equal to a counter. Call this A. The one shot of A is the same as the signal for A with a counter. These are equal. Some people like doing counters with counters. Some people like doing counters with one shots and adds. And you may choose. Good. Take care. We're working on Chapter 7, the timing program for the stoplight, and we're going to start with a simple 6 timer segment, and I'm going to put those together for you first. And in order to do that, I'm going to create a couple of lines of logic, and I'm going to show you how those lines of logic can be used to give us 6 segments of time. So I'm going to start with a normally closed contact. I'm going to call it B5 and put a name to it, B5. Right click and define tag and call it a global memory, M0.0. So it's going to define that as global memory, M0.0. So we now have a bit, it's just a control bit, but we're going to use that in a way that we're going to show you in just a little bit. So just hang on. So now we're going to go over and we're going to get a TON timer. We're going to pull it over. We're going to put it next, and we're going to call that timer 1. Timer 1 is the first segment of time that we're going to use, and it's defined here, but we're going to put in the preset. We're going to use 3000. That's 3 times 10 to the minus third, or 3000 times 10 to the minus third seconds, or
3 seconds. So that's going to show us 3s, or 3 seconds. It's going to give us a time delay of 3 seconds. So from the time the signal comes in till the time the output turns on is 3 seconds. We're going to skip this elapsed time. We're going to not use it at all. We're not going to come up and put a coil after the timer. I'm going to put it up here. And we're going to use the bit, another control bit, B0. So we're going to use a control bit, right click, define tag, and again, go with a global memory. And it's going to roll to the next bit, M0.1. So now we have 2 control bits and 1 timer. And we're going to come over and pull another timer in here, and we're going to put it after the B0. I'm going to call it timer 2. Now we've got a control bit, a timer, a coil, and another timer. This one's till timer 2. We're going to do the same thing with it, 3,000 milliseconds or 3 seconds. Leave the elapsed time alone. We're going to come up here and do another coil. And you guessed it, this is going to be B1. And right click, define tag, and it will roll to global memory M0.2. And we're going to get a third timer, and we're going to put it right here, and we're going to call it timer 3. And then 3,000, and forget about the elapsed time, and we're going to bring a control coil again down and call it B2. Right click, define tag, global memory, M0.3, define. So we now have in our program a set of 3 timers and 4 control bits. Now we're going to bring the contact off of that control bit B3 or B2 down, excuse me. I'm going to bring B2 down, contact off of it. And we're going to start another timer. It's going to be timer 4. So we're going to go over, all these are TON type timers. They're going to be a delay after the input turns on, after the IN turns on. And again, we're going to use 3 seconds. And ignore the elapsed time. And we're going to put another bit in coil, call it B4. Right click, define tag. Again, global memory, M0.4. Another one, we need 6 altogether, so we're going to keep going here. Timer 5. Another control bit, and I got it in the wrong spot, so I have to bring it up here and try to turn screen, and it will take. So now I am at B5. And excuse me, I got this one off by 1. This should be B3. This should be B4 right here. Should be B3. And so now I've got B2, B3, B4, and then I've got one more timer, one more time delay. I need 6. It's going to be timer 6. And here's my B5. So I'm going to bring in my B5 right here. So I now have 6 timers and I have 6 control bits, and this is how it looks. So I'm going to get rid of this little fellow right now. I'm going to transfer this program over to the programmable controller. I'm going to come up here and compile. I'm going to download it. It says error during compilation. I got to go back and find my error. So there is an error here. I didn't put my numbers in here. So I've got to go back and do that. I'm going to go back and compile. Download. Consistent download. Go online. These all turn green. That's good. Now I can do my glasses. And I'm beginning to look at this thing and see what's going on. Now I'm going to bring this over to the full size of the screen. And we're online. And as we look at this, what do we have? Each of these, as they liven up, you see them moving. And then when the last one turns on, it crashes and it turns off this one over here, and then it starts all over again. So we have 6 recurring timers, each of 3 seconds in length. And we can use these bits, these control bits, to control our lights when we have our traffic lights. So we now have timers that work well. And all we got to do now is to start writing logic for them. Okay, so let's go back to the offline. Go offline. And we're going to add some logic. And we're going to start with in the same rung, or in the same network, we're going to start with a green light. Okay, so the green light for the first direction would be not this timer being done. In other words, while this timer is timing. So we would say something like this, not of B0, because that would be when this timer was working, but not timed out. So we would just use the not contact up here, bring it down. I would say not of B0. And that would give me an output, a coil, and that coil would be a Q output, and we can call that Q 0.0. We can call it whatever we want to, but it's a discrete output. And instead of assigning it the word tag, we can rename it. We can call it green, north, south. So that changes it to a name that we can understand. Now we're going to go and we're going to do the yellow, which would be the next timer with this timer right here. So that would be not this, but this one. So we would write that one as B0, normally open, B0, but not B1. See how that works? That would be B1. So we would say this timer timed out, but this one not timed out would give us an output that would be the yellow. And that would be Q 0.1. And again, we want to give it a name that's meaningful, so we rename it. Call it yellow, north-south. And I'm not going to do them all for you, but you get the pattern. This is a pattern of how you can do these. Now I'm going to go down here and add the red. So what would be the red? Well, one way of saying it would be this or this or this or this or this, but you could also very easily say it's the not of green and the not of yellow. And you can say that would be my red, and it is. That's a good way of putting red is when it's not green or when it's not yellow, it's red. So you're going to type this one as Q 0.2. Now again, if you're doing this with an HMI, you do not want to type in Q, you want to type in another internal tag, another M tag. The Q tags are output tags, and these are going to take it to a screw terminal on the output, which you can wire to a light. I'm going to say red, north, south. And that gives me my three, whoops. I wanted to define the tag as a, not as a local tag, but as a global. And I want to type it in as a Q. Okay, so that would give me there you go. Rename it so that it's not the same. Okay, I'll give it another name. Okay, that. I want to go back to my tag base and get rid of those two tags so that I can start again with those two tags. So just delete these two. Make a mistake many times, deleting is the best way to go. And I want to say here Q 0.2. And then it's going to go back and it's going to say rename. I'm going to say rename tag Q0.0. Set tag one, I want to say red north south and see if that works. Hopefully that works. Okay, that's good. So we're now going to try this function, and again we're going to compile it. We're going to download it. See if it works. Go online. We're going to watch these three. We're going to go online. We're going to say, get the glasses on. Okay, so here we are. We're in this portion of the program. And we want to look at all of this going on as best we can. And we can't see all of it quite, but we can see most of it. You can see with these timers up here timing. And as we go through the timers, here we are, this one. When this one turns on, okay, now we're back and the green is on. Then the yellow is on. Then after that, the red turns on. And now if you do this for the other two directions, your turn lane and your east-west lane, you would have satisfied the majority of this lab. So we're going to go back. We're going to add some more logic. This would be the logic for the item having to do with the turn lane giving extra time. So we're going to talk about adding logic now. So when you are in a specific timing portion, let's say this green time here, you want to add some logic that says what? I am having a lot of traffic go by fast, or I'm going to have a traffic go by slow. So here we are. We're going to say I'm in the I'm in a certain period of time, and I can look at that and I can say, okay, now I'm going to say that by doing this. I am in the time period 1, which would be the not of the not of B0. So not of B0, and that would be when I'm in timing period 1, so I'm going to say B0. Okay, now I'm in that timing period, and I have something that goes by. In other words, I have an input. I have a device that turns on. Okay, so let's say this is an input, I 0.0. So in other words, I have a tire that went by, and I saw that tire. So this would be a car going by. I see a car going by. Now, that's information. So I'm in the timing period, and I have that. So I'm going to now go back, and I want to say I'm going to put a seal circuit or a memory circuit around that. So I'm going to tie that to a bit called A. Okay, so this says there's car in zone. So car in zone, we're just going to call it car in zone. So that's going to be our bit. It's a memory bit. Define it. Not a local. You can't use local. You've got to use global, and it rolls it to the next bit, M6. So now we're going to tie this back to here. So this is going to be a seal circuit. I'm going to get rid of this one I'm going to leave it for some later. But here we are. Now we're going to say, okay, so we're going to tie this to this coil that says car in zone. Now we have information. So we now know there's a car in a zone. And we're going to say that if there is a car in zone, in other words, a car is in the zone, and there's not an input for a period of time. So we're going to use the not of the input for the car in zone. So we're going to say we saw a car in zone, but now we've not seen a car in the zone for a while. So in other words, no, we haven't seen the input. Excuse me, we haven't seen the input. Okay, this would be a car passing. I'll just say car passing. Rename car seen. Car seen. Okay, but not a car seen. In other words, we have a car. We've seen a car, but now there's not a lot in there, and they're going by rather slowly. If that's the case, what do? Well, we time this out, and if we time it out, we put in a TON timer here, and it says time cars slow. Okay, so this would be a slow boat. In other words, we've got cars, but they're not going by very fast. Let's go 2,500 for our. That's 2.5 seconds. So they're slow. They're going by, but they're slow. So if that happens, what do we want to do? Well, if we get done with this, we're going to move a bit. This is a very moving process here. We're going to move a bit into. We're going to move a longer number into that preset. We're going to move a number like 6,000 into that preset for that one up here. But now we cannot say 3 anymore. We've got to say timer 1 preset. So we make it a variable. So you have to make it a variable, and you right-click, define tag, and it is not a local temp. You want to make it a global, and it assigns it automatically as a MD. You've got it. So now we're going to come down here, and we're going to move 6,000 into timer 1, and that's timer 1 preset. Okay, so we've got that. Now we've now moved a longer number into that. Now, the only other thing we have to do to get this to work is to, when timer 1 is done, or when B0 turns on, okay, so when we see B0, we reset the preset back to the original number. So I'm going to take another move, and I'm going to move 3000, the old number 3000, back into the preset. So timer 1 preset gets a longer number for a short period of time, and then it goes back to its original preset, and we're waiting for the next turn around. So this gives you some ideas, maybe how to attack that. If that's the process you were going to be working on, that would give you some ideas on how to address that. It's not the only one. There are many ways of doing that one, but that gets you at least started on that particular subject. Okay, so we're going to now go on and look at a new project, and this is the Whopper combo counter for the McDonald's cash register. So we're going to do that next. So we're just going to wipe all this stuff out. We're just going to clear this all out here. Delete, 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 and we're going to try to get it all out of there. And start from scratch. Let's see if we can get something going here with okay, so we're back to a fresh screen. Now the Whopper combo is a counter, and it's a counter that we can both count up and count down. So we come over here to our counter operations. We get rid of we don't think timers anymore, we're thinking timers. So we're going to go to the timer or counters. And we're going to come down here, and we're going to get the counter that goes counter up or downer. Okay, so we're going to do that. We're going to bring it in, and we're going to call it Whopper combo. Okay, so we're going to try to put a combo timer. Now we've got all these things here that we can put in front of it, and for right now I'm just going to put the B0, the B1, and the B2 in front of it. And we're going to try to make this thing work. So we're going to bring a contact down here called B0, B0, okay, B0. We've already got it defined, so that's going to be our bit that counts up. B1 is the one that counts down. When it turns green, you can turn it on. So basically, you've got to wait. B1 is the bit that turns it on. B2 is the reset bit, so we're going to come down here and do the reset bit. Now, reset is the one that resets the whole counter, so we're going to do that, B2. And then the preset here is the PV, and we're going to say a big number, 9999, something that's so big we don't really care. And for right now, our output is whatever, it doesn't really matter. But we're going to come back and we're going to call that Whopper combo count. So we're going to try to even put that in now. We're going to, this is a number that we're going to need later on. So we're just going to define it right now, and we're just going to leave it. Okay. So it's an int. We're just going to use it as an int, and away we go. So this is a counter, and let's see if we can get this to work. So we're going to go over here and compile it, download it. See if we got it now. Okay, so now all I have to do here is to toggle this bit. It says modify to a 1. And if I turn that on, now watch what happens. The counter goes to a 1. And our number in our Whopper combo count goes to a 1. I got to turn that bit off, modify to a 0. But I can try this from right here. I don't have to go someplace else or whatever. Now, this can either be an input from an I. I can actually have a button, or I can have a button, or I can have it from an HMI program. So either way, it works. Okay, so if it's an internal, it would be an M. If it's an I, it uses screw terminal. Okay, so if I want to cancel that and go to back to 0, I turn. Okay, so I counted to 2. Sorry about that. Modify back to 0. Now I've got it 2. Now I come down here to my down counter, modify it to a 1, and it went back to a 1. Does everybody see that it went back to a 1? So I'm now going to go back to modify that one back to 0. You got to turn them all. You always got to turn them off. Now let's go back to a 2. Let's get 2 in here. Modify to a 1. And if I want to reset it to a 0, I just go down here and I reset it to a 0, and it resets it even with the counter on. See that one? This is a reset is an override for everything, and it knocks everything out. When you reset, you go back to 0. As long as you hold it on there, the counter's not going to count. Okay, so also in this, we are going to calculate how much we had, how many that we had, and we're also going to say we're going to have some logic that counts down. So when you have the logic for counting up, we had one button for all of the countdown, and we're going to go back offline. We're going to develop that logic next. So we had one button for each of the 6 items going up, but if you have the whoops button or the countdown button, you only had one. But here you would have to have 6. So we're going to have to store some information and remember something. So when you hit B0 here, when you hit B0, you want to store a number someplace. So you say B0. This is giving us the memory that it says this was the last thing that we hit. So we're going to use another move instruction to a number. We're going to say we're going to move 1 into the number last, or last hit, or whatever. We're going to call it last. Okay, define this as a memory global, and not as a byte. We're going to call it a what? We're going to call it a variable. Call it an int, or we could call it a dent if we wanted to. I'll just call it an int. Define it. Okay. So now we know that the last thing that was hit was Whopper combo, as opposed to drink or something else. So now when we hit the B1 button, instead of B1 being hit, we could say cancel last, which would now, let's just call B1 cancel last, change the name. Okay, so we're changing the name of B1 to cancel last. Okay, so we're going to say cancel last. Okay, and this idea that the last thing that we hit was a 1. So that we have to use a comparative statement. So we come down here and we find an equal, and we say last equaled a 1. The last thing we hit was a 1. So only time we hit cancel last and last thing we hit was a Whopper combo is just going to actively move over there. The other thing we want to do is we also want to guarantee that this does not go past 0. So in other words, we want to make sure that our count is positive when we do this countdown. So we have to do a comparison statement there, and that is a greater than. We say Whopper combo count is greater than 0. This is just to protect us from owing the person some, this counter can go negative, so we really don't want it to go negative. So we only want to count down as long as this thing is positive. That protects us from that. Okay, so that gives us that logic. Now we're going to come down here and we're going to do some math. And the math is not hard, but we have to use a calculate instruction for it. We're going to find the math functions right here. Okay, math. We're going to use a calculate block. It's the best one we have, so we're going to use it, even though all we're doing is multiplying. So it's count times amount, and we're going to type, the output is going to be a word called total. Okay. The type is going to be int or real. Let's start from. I'm going to pick the type here. So we're going to pick this as a real. Okay, the output is going to be one called total. Okay, so we've got to define. Okay, so this is the one where I say total. You define this as a number. Define tag as a global real. And the inputs are going to be whopper combo count. And then a price. So the price would be, I don't know what a whopper today costs, but let's just say $4.95. Now you could have a variable there as well. Now the output is going to be in 1 times in 2. We're done. Now if I want to add more, if it would be in 1 times in 2 plus in 3 times in 4, in other words, if you have a bunch of them and you want to string them out, you just click this little insert and you get more. I'm not going to do that, but as you add more logic, you're going to have to click this little insert button and you're going to have to add more of these inputs. You get as many inputs as you want and they just keep stringing down on the left. So let's try this. Download. Classes. Okay, so now I am at 0. I'm going to go up 1, modify by 1, bump it up by 1. Okay, now I have a count of 1 in there, and I also have my last is 1, and my calculate says I now have a total of 495. I'm going up here and I'm going to do another one. I got to go off. I got to go to 0. I got to go 1 again. And now I'm at 2. And now if I'm at 2, I go down here and I see I'm at $9.90, which is exactly what I have. If I want to go down here and cancel last, I go backwards by 1, modify to a 1, and it should take me back to a 1, even though this is on. Okay, so now I'm back at 1, and I'm back at $4.95. So this works. And the last will work if you add more ingredients. So basically, this program is up and running. So as far as the Siemens side, it looks pretty good for these two labs, 7.1 and 7.2. Gives you some ideas how to start and do these labs. I want to very quickly switch over my port to the Allen Bradley side. We'll take off and do some Allen Bradley programming. Okay, so I'm going to go over here and plug into the Allen Bradley side. Now we're live, not live yet, but we're going to get live here in a second on the Allen Bradley side and do the same programming on the. We're back with Allen Bradley, and we're going to begin to look at the timers. So again, we're going to add a rung. With Allen Bradley, you always have to start with adding a rung. Then we're going to start with a timer this time. We actually start with a TON timer, and we're going to bring it down, and we're going to assign it the value timer 1. So we type in the word timer 1, right-click, new timer 1, click create. We put in a preset, 3000, same as we did before with Siemens. Now we have a problem in that the EN, enable, is tied to the output. So we have to use the ability to create a contact off of timer 1 to allow the delay. So now we're going to go back under favorites, pick contact. I'm going to come back here. I'm going to pick a contact that basically ties this and says timer 1 dot done. Okay, now we have not only the timer but a delay that now allows us to go to the next timer. So we're going to pick another timer, timer 2. Same thing, right click, new timer 2, create, 3000, enter. So now we come over here, we go back under favorites, click another one, timer 2, not done. We come back under timer again, timer 3. Okay, right click on timer 1, create 3000, and away we go. Now we have 3 timers setting here. We really want to have 6, so we're going to come down here and we're going to add some more. So we're going to click on favorites, normally open, and timer 3, not done. So now we are tying the output of this timer to this bit right here. So we're going to come in with another timer. Timer 4, enter, right click, new timer 4, create 3000. Come over to the right of it, under favorites, pick the contact, timer 4, done. Click on the timer again, TON, timer 5. Right click, new timer 5, create 3000. Over to the right, contact, timer 5, done. And then we come over under timer and do another timer, and this is timer 6. Right click, new timer 6, create 3000. And we don't need a bit out here because the done bit is all we need. So we're going to come up here at the very beginning of this one. We're going to add a contact under favorites. This would be a normally closed contact instead of normally open, so we're going to have to get a normally closed contact. Oops. Right here, normally closed. That would be timer 6. Not done. So we've now got 6 timers, and they should cycle through. So we go on up here and do a download. Watch it and see if it works. And we want to go back to the run mode, and we don't have to do anything, no glasses or anything, and we can just sit here and watch. And as we're watching, we see the numbers going up. This one right now, now this one, now this one, now this one. Watch what happens when it gets done. Goes back and starts at the first one. I'll let you just watch that for a second or 2 or 3, and you can sit here and you can observe these timers going through the cycle of 6 cycles. Okay, we're going to go back offline. And we're going to go back under favorites, and we're going to start with another one. This is going to be the green light. So this would be when this timer is timing, and we don't need any B or whatever. We can just say timer 1 timing. Okay. Timer 1 dot TT, timer 1 timing. And then I can put an output over here, which is a coil, which should be, click on this little guy right here. Look over here on the right. Now I go find an output coil, which is a physical output. Click on this little guy right here, and it brings up this little int. So I go to int local 1 output.data 0. So basically that is my output for my first one. And it already popped up with a green, but I'm going to edit. I'm going to show you how to edit description. And it says that one is green. So we've got the green. I'm going to change it to green north-south. So we now have the edit for the green north-south. Now how do we do the yellow? Well, the same way. We're going to do another rung. Timer 2. Timer timing. Over here is a coil. Go fish. This is an output as well. Expand it again. This would be bit 1, or whatever you want. It doesn't have to be but 1. And again, I already had the yellow, but I'm going to edit the operation. I'm going to say yellow north-south. Okay, so we now have a, they have those two, and we're going to do the red, which would be what? The not of timer 1 and not of timer 2, or we could do that way. That would be a nice way to do it. So let's do it not of timer 1, timer timing, and the not of timer 2, timer timing. That would be my red. So let's go ahead and put a coil. And that would be local output, embedded output, local 2. And that would give me my red. Right click, edit instruction, red, north, south. All right, so we now have the 3. And I'm going to go ahead and put in the logic for the input. So this would be the logic for the changing the like we did before, changing the preset. So in the favorites, get another coil there. And this would be a timer 1 timing. I'm just going to go up here and Control C, Control V. Timer 1 timing. So I'm in the green cycle of the timer that I'm letting the cars through, and I have a contact. Okay, so this contact would be what? This is an I. This would be an internal input bit, and it's an I, local data I. And it'd be bit 0. If you want to, you can do something else with it. Right click on this. You can edit the description if you want to of the edit. Okay, Control V. Okay, so edit later on. Not, okay, I don't want that. I want edit main operand description. So I want to say this would be car in process. Okay, so this would be a car in process. Okay, so that would be that. And then I say, okay, coil or an output coil. Here, Ted. This would be car in, okay, car remembered. So I remember, I saw a car and I remember the car. So basically I remember this and I have to do something to seal the deal. So I have to seal it with a car remembered. Right click on this one right here. To make that a bool first. Car remembered. Okay, so that's my car remembered bit. So now I say, I remembered I saw a car. Okay, now I saw a car, but I also did not see it again for a while. So again, I do not see it for a while. So now I want to say, on top of this, I want us to say, throw a seal circuit in there. Okay, I saw it, but I'm not seeing it again, and I'm saying absence of car. I want to say this coil right here. I'm going to change this to an NIO. So I saw it, but now I'm not seeing it for a while, and if I don't see it for a while, I'm going to do a move, and I'm going to move something. I'm going to move a bit I'm going to move a preset into my, if it's slow, I'm going to add some time. So I'm going to do a move. Okay, so I'm going to move. I'm going to move 6,000 longer time base into my what? My timer 1 preset. And then I also have to say when I am done with that, I have to move it back. So I have to reset it to timer 2. So see, okay, there's my timer 2. I do a move of a 3,000 back to my preset. So I move 6,000 in if I see it, but then I don't see it for a while. In other words, we're really slow. And it may work, this might not work, but at least it gives you something to try. And I would suggest you try this and see if it doesn't work. If it does work, maybe you want to modify it a little bit, but at least it gives you something to look at. Okay, now we're going to go down and we're going to talk about our counter for a little bit. And I'm just going to keep on going here. This is totally separate from the above program, but we're just going to keep on going. We're going to forget about that program up there, and we're going to go on down. So we've got a counter here that we did have a thing called B0. And I'm going to go back and we're going to look at those. Okay, so this would be my B0. This would be from the same thing we had from Siemens land. Okay, so we're going to new B0 here. Okay, so this is if you hit the button for whopper count. So now we're going to go and we're going to do a counter, but this is, we do not have a counter up down, so we only have a counter that goes one way. So we're going to say if you want to count up, it's whopper combo. Whopper combo, okay? And preset, make it a big number, 9999. Oh, we've got to declare it first. New whopper combo, create. Now I can put a preset in. Okay. Now if I want to count down, remember this, we had to do that, all that stuff. So now if we counted up, we had that thing called last. So let's just put a, around this, let's just put a rung or a ring, a loop around it. And then I can say, if I counted up, I wanted to put a 1 in the word last. So I want to move a 1 into the word last. Okay, so I want to do that now, new word last. So I want to create a word called last. So now I've got this one up and it's running. Now, if I use the same name, but with a countdown, I have to put another rung in. But, okay, so I'm doing that. So if I put in a B1, okay, so I'm here, do a B1, but this would be my cancel last. Let's just call it cancel last. Okay, cancel last, new cancel last. And it equals 1, so I have to put an equals in there. A compare statement equals last equals 1. And I'm greater than 0. So to a compare statement, it says greater than 0. Okay, so my whopper count dot ACC is greater than 0. Then I can count down. Whopper 9999 is, you can count down. So if I have 1 and 1, one count up, 1 count down, it works the same as the count up, count down with Siemens. So basically that gives me my logic for my whopper combo. Now all you have to do is the same thing for your other 6 items and you're done. Now the calculate line is a little different. It can run all the time, and it is a compute block. Compute till you puke, if you want to call it that. It's however you want to remember it, but that's how I remember it. Total, the variable, you have to say new. You have to decide what type it is. It takes any type. Now the expression here is something though. You have to say whooper cbo.acc times 4.95. If you want to say that, you can. If you don't want to, you don't have to, but it compiled and it worked. So let's try it. Now we've got two programs running here, and we're going to look at them both as we do this. So let's download and see what we got. Okay, so here we are with our logic for our count or for our the traffic intersection, and our green, our yellow, and our red. Okay, this is our car instruction. It sets up a bigger line. If we want to, I'm gonna let you check that out and see if you can. If it works, if it doesn't work, you can try it out and see what you think. If it doesn't work, then you can change it, or you could go to another option. Okay, so now we're looking at the counter here, and right now this would be if you hit the button for whopper. I'm going to toggle a bit. All I have to do is toggle a bit, and look what it did. It went to a 1. The accumulated value in whopper combo is a 1, and my word last is a 1. I'll toggle it off. What you got to do here is remember the toggle bit. Toggle it again. This went to a 2. This stayed at a 1. And my number for my total here should be what? It doesn't really show what total is. But now I'm going to go down to my other area right here. And I'm going to show you how to look at that area. So this is my word total, and monitor it, and I can see whether it's changing at all. And it went in as a dent. I should have said it as a real, but it went in as a dent, which rolled it over to a 10 instead of a 9.9. But if I wanted to go back, and I could, I'm not going to, but it's a minor error. But anyway, I'm going to go back to my program. Now, if I wanted to monitor that, I could, though. See, it's there. So my ability to also to look at this whopper combo and see these numbers in here. Here's my accumulated value, my preset, my accumulated value, my count up value, all that kind of stuff. And there they are. Let's go back to the main routine. So I made an error. I got total as a dent, and it rounded it off. But that's okay for right now, but you should have that as a real. And that should get you going on those two labs. Take care and have a good day.